The assertion that a light bulb's heat output is directly proportional to its wattage and remains constant between halogen and regular incandescent bulbs is generally accurate, with a nuance. While both bulbs of the same wattage consume the same amount of electrical power, the efficiency with which they convert that power into light versus heat differs slightly. Halogen bulbs operate at a higher filament temperature due to the halogen cycle, which allows them to produce more light for the same power input compared to standard incandescent bulbs. In essence, a halogen bulb is a more efficient converter of electrical energy to light, meaning it dissipates a bit less energy as heat for a given light output. An experiment comparing a 75-watt halogen bulb to a 75-watt incandescent bulb showed a slight difference in temperature. The halogen bulb measured 230 degrees Fahrenheit, while the incandescent bulb measured 250 degrees Fahrenheit. This difference suggests that the halogen bulb, while consuming the same power, converts slightly more of that power into light, resulting in a lower overall temperature. To delve deeper, it's crucial to understand how incandescent and halogen bulbs generate light. Incandescent bulbs produce light by heating a filament until it glows. This process is inherently inefficient, as a significant portion of the electrical energy is converted into heat rather than light. The filament temperature dictates the color and intensity of the light emitted. Halogen bulbs, on the other hand, incorporate a halogen gas such as iodine or bromine within the bulb's envelope. This halogen gas participates in a chemical reaction known as the halogen cycle. As the filament heats up, tungsten atoms evaporate from its surface. In a regular incandescent bulb, these tungsten atoms deposit on the bulb's glass envelope, causing it to blacken over time and reducing the bulb's light output. In a halogen bulb, the halogen gas reacts with these evaporated tungsten atoms, forming tungsten halide molecules. These molecules circulate within the bulb until they come into contact with the hot filament. The high temperature of the filament causes the tungsten halide molecules to decompose, redepositing the tungsten atoms back onto the filament. The halogen atom is then free to react with another evaporated tungsten atom, continuing the cycle. This halogen cycle offers several advantages. Firstly, it prevents the blackening of the bulb's envelope, maintaining light output throughout the bulb's lifespan. Secondly, it allows the filament to operate at a higher temperature without rapidly deteriorating. This higher filament temperature results in a whiter, brighter light compared to standard incandescent bulbs. Thirdly, it improves the bulb's efficiency, as more of the electrical energy is converted into light and less into heat. Now, let's consider the factors that influence the heat output of a light bulb. The primary factor is the bulb's wattage, which represents the rate at which the bulb consumes electrical energy. All that electrical energy is converted into light and heat. The efficiency of the bulb determines the proportion of energy converted into each form. Inefficient bulbs convert a larger proportion of energy into heat, while more efficient bulbs convert a larger proportion into light. Several factors affect a bulb's efficiency. These include the filament material, the gas fill, and the bulb's design. Filaments made from materials with higher melting points can operate at higher temperatures, resulting in greater efficiency. The gas fill can also influence efficiency, as certain gases can help to reduce filament evaporation and improve heat transfer. The bulb's design can also play a role, as factors such as the shape and size of the bulb can affect its ability to radiate heat. To illustrate the difference between halogen and incandescent bulbs, let's compare two bulbs with the same wattage, say 60 watts. A 60-watt incandescent bulb typically produces around 800 lumens of light and has a lifespan of around 1000 hours. A 60-watt halogen bulb, on the other hand, produces around 1200 lumens of light and has a lifespan of around 2000 hours. This demonstrates that the halogen bulb is more efficient, producing more light and lasting longer while consuming the same amount of power. Now let's address the question of whether a temperature sensing tester can accurately measure the heat output of a light bulb. While a temperature sensing tester can provide a relative indication of the bulb's temperature, it's important to note that it doesn't directly measure the total heat output. The temperature measured by the tester is influenced by several factors, including the bulb's surface emissivity, the ambient temperature, and the distance between the tester and the bulb. To accurately measure the total heat output of a light bulb, a more sophisticated method is required, such as using a calorimeter. A calorimeter is a device that measures the amount of heat absorbed or released during a chemical or physical process. To measure the heat output of a light bulb using a calorimeter, the bulb is placed inside the calorimeter and the calorimeter is sealed. The bulb is then turned on and the heat it produces is absorbed by the calorimeter. The calorimeter measures the temperature change of its contents, which can then be used to calculate the total heat output of the bulb. In conclusion, while the statement that a light bulb's heat output is directly proportional to its wattage is generally accurate, it's essential to consider the efficiency of the bulb. Halogen bulbs are more efficient than regular incandescent bulbs, meaning they produce more light for the same power input, resulting in slightly less heat output. A temperature sensing tester can provide a relative indication of the bulb's temperature, but a calorimeter is required to accurately measure the total heat output. Several factors influence a bulb's efficiency, including the filament material, the gas fill, and the bulb's design. Understanding these factors can help to choose the most efficient lighting options for specific needs. It's also worth noting that other types of light bulbs, such as compact fluorescent lamps, or CFLs, and light-emitting diodes, or LEDs, are even more efficient than halogen bulbs. These bulbs produce significantly more light and less heat for the same power input, making them a more energy-efficient choice. For example, a 15-watt LED bulb can produce the same amount of light as a 60-watt incandescent bulb, while consuming only a fraction of the energy. Furthermore, LED bulbs have a much longer lifespan than incandescent or halogen bulbs, lasting up to 25,000 hours or more. When considering the energy efficiency of different light bulbs, it's essential to look at the bulb's lumens per watt rating. This rating indicates the amount of light produced per unit of power consumed. Bulbs with higher lumens per watt ratings are more efficient, producing more light for the same amount of energy. In addition to energy efficiency, it's also important to consider the color rendering index, or CRI, of a light bulb. The CRI indicates how accurately the bulb renders the colors of objects compared to natural sunlight. Bulbs with higher CRI values provide more accurate color rendering. Finally, it's crucial to dispose of light bulbs properly. Incandescent bulbs can be disposed of in the regular trash, but CFL and some LED bulbs contain small amounts of mercury, which is a hazardous material. These bulbs should be recycled at a designated recycling facility. By understanding the different types of light bulbs and their characteristics, it's possible to make informed choices about lighting options that are both energy efficient and provide the desired light quality. It's also worth noting that the heat produced by light bulbs can have a significant impact on the overall energy consumption of a building. In the summer, the heat from light bulbs can increase the load on air conditioning systems, while in the winter, it can help to offset heating costs. Therefore, choosing energy-efficient light bulbs can help to reduce energy consumption and save money on utility bills. To further elaborate on the experiment, consider the conditions under which the temperatures were measured. Were the bulbs enclosed in a fixture, or were they open to free air circulation? An enclosed fixture would trap more heat, leading to higher temperature readings for both bulb types. Air circulation would dissipate heat, resulting in lower temperature readings. The distance at which the temperature sensor was held from the bulb is also critical. The closer the sensor, the higher the reading, as the sensor is directly exposed to radiant heat. The experiment should be repeated multiple times, with careful attention to controlling these variables to obtain more reliable and statistically significant results. Consider measuring the surface temperature at multiple points on each bulb, as well as the ambient temperature surrounding the bulbs. This data would provide a more complete picture of the heat distribution and heat transfer characteristics of each bulb type. It would also be beneficial to measure the power consumption of each bulb using a wattmeter to confirm that they are indeed drawing the same amount of power. Differences in manufacturing tolerances or voltage fluctuations could affect the power consumption and thus the heat output. Additionally, it would be useful to measure the light output of each bulb using a light meter to quantify the difference in light output between the two bulb types. This would provide further evidence of the halogen bulb's greater efficiency in converting electrical energy to light. Furthermore, The type of temperature sensor used can influence the accuracy of the measurements. Thermocouples, resistance temperature detectors, or RTDs, and infrared thermometers each have different characteristics and limitations. Infrared thermometers, for example, measure the temperature of a surface by detecting the infrared radiation it emits. The accuracy of an infrared thermometer depends on the emissivity of the surface being measured, which is a measure of how efficiently the surface emits infrared radiation. Different materials have different emissivities, so it is important to know the emissivity of the bulb surface to obtain accurate temperature readings. The statement is generally accurate but with nuances related to efficiency and measurement considerations. A more comprehensive analysis would involve careful control of experimental variables, precise measurements of power consumption and light output, and consideration of the limitations of the temperature sensing equipment used. In summary, while the wattage equivalence suggests similar heat production, the halogen bulb's increased light output for the same wattage leads to a slightly lower heat dissipation compared to an incandescent bulb. Precise measurement and experimental control are critical for accurate comparison. Also consider the long-term energy savings and replacement costs. LED typically lasts significantly longer, leading to fewer replacements. Also, consider the environmental impact. LED do not contain mercury, which is present in CFL, making LED a more environmentally friendly option.